Alright, we're continuing on with chapter 5. This is going to be solving compound inequalities. So, what is a compound inequality? First thing is, what is a compound statement? So, anytime you have two or more simple statements connected with and or. So, anytime you give someone a choice, do this or do that, or anytime you say bring this and bring that, you're making a compound statement. You're requiring them to consider two different pieces of information. So, for an and statement, the overall statement is only true if both things are true. If you tell someone, bring a coat and an umbrella, they only succeeded in accomplishing the task if they bring both the coat and the umbrella. However, for an or statement, it's true if at least one part is true. If you say, bring a coat or an umbrella, they succeeded in your task if they just bring a coat, or they succeeded in your task if they just bring an umbrella, or they could even bring both and they still succeeded. So to succeed or have a true or statement, you just have to have any part of it be true. But for an and statement, you need both things to be true. So we're going to apply this kind of general idea to math and inequalities. So a compound inequality, instead of just a compound statement, is two or more simple inequalities. This is something with a less than or greater than sign, grouped together again with and or. So if you're dealing with an and inequality, what you have is called an inequality intersection. So where the two statements intersect is the region where your solution is. So here's the definition. The region where multiple simple inequalities are all true and the graph of those inequalities overlap. So the region where both simple or multiple simple inequalities are all true is where the inequalities intersect. On the other hand, if you have an or inequality, you just need any part of it to be true. So an inequality union is the total combined solution for all of the different inequalities that are being involved. So a union is typically expanding your answer, making it even bigger and more inclusive, whereas an intersection is reducing or restricting your answer to just the areas where stuff overlaps or is both true. Okay, so problem solving tips. How do you deal with these kind of inequality compound statements? The first thing to do is fully simplify or solve each of the individual inequalities first. So you might have blah 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 and blah blah blah. So those two first and second inequalities, you want to completely solve them first, and then you'll graph the solution to each of those different separate inequalities, but you'll graph them both together on the same axis. Okay? And then if it's an and statement, you want to see where those two overlap or intersect. And if it's an or statement, you want to see where those two or where the union is, which means the combined answer of everything that's shaded from either one. And your final answer will be written, if it was an and statement, you're going for the intersection. You're going to write your answer as, so let me show you on a number line what this looks like. So for example, if this one is shading this way, and this one is shading this way, then here's your lower number, here's your large number. The only place where both of them are shaded is in between. Okay, so you're larger than this number and you're smaller than this number. So typically an and statement will have a lower number and then a less than sign and then your variable and then a larger number. So basically that should be a number sign, sorry. It should be in between these two things. So you can say my variable, say x, is in between this number and this number. That would be my solution. On the other hand, an or statement is the union of two separate. So you might have this one shaded this way and this one shaded this way. So for an or number, you're saying I'm including this part and I'm also including this part. So since you want to include both, you use or so that it's either one is true. So you say the variable is less than this lower number or greater than this larger number. And so here your graph is restricted, here your graph is expanded. Let's do a couple of examples. Solve and plot the solution. 5x minus 3 is less than 8, and 3 minus 7 times 2 minus 5 is less than negative 3x plus 2. So the first thing we need to do is actually just solve each of these separately, so you get a lot more practice solving your inequalities. So we'll go plus 3 plus 3. That gives me 11. 5x equals 11. Divide by 5. Divide. Oh, not equals. Sorry. I get in a habit, and you might also, when you're doing equations, you just naturally think of it as an equal sign. So be very careful that you keep whatever this was. So less than x is less than 11 fifths. And then we have and. Okay, we've got to solve this one here. So we need to simplify this side first. This is a whole bunch of numbers. There's no reason to start solving until we get this down to a single number. So a lot of you are tempted to start by doing 3 minus 7 is negative 4, but you have to be very careful because that's not following PEMDAS, even though it's tempting. So PEMDAS says start with the parentheses. 2 minus 5 is negative 3. Okay, multiplication comes next. 7 times negative 3. So we have 3 minus 7 times negative 3 is a negative 21. 3 minus a negative becomes 3 plus. So this is a grand total of 24. Again, not equals. Sorry, we have this less than sign again. Negative 3x plus 2. Now we're ready to solve. Minus 2 minus 2. 24 minus 2 is 22. Is less than negative 3x. Divide by negative 3, divide by negative 3. And here, be paying special attention, we divided by a negative. So we have to flip the inequality. So negative 22 thirds. Flip this inequality is greater than x. And now you can see here. Okay, so we're back in action here. And we were noticing that because we divided by a negative, we had to flip this inequality. And then the other thing is, typically when we write our inequalities, we put the variable on the left. So I'm just going to switch this sides. So this is x is less than. See how the point is pointing towards the x? So if I switch these two things to the other side, I have to obviously change this. So this is x is less than this stuff, or this stuff is greater than x. So x is less than this stuff. Okay, so here's part of my answer, and I have an and here's part of my answer. So the question is, what's my overall final answer? So the way that we do this is we make a number line, and we plot the two solutions. So this is 11 fifths, and this is negative 22 thirds. So that's over here somewhere. Negative 22 thirds. And let me change colors. And so we want to see, because it's an and, we want the intersection where these overlap. This one is less than, and it's excluding the endpoint. So we're shading that way. And this one is also less than. So we're open circle, and we're shading that way. Okay? So now look at it like this. If you're over here, you're not less than either one. If you're here, you're less than this one, but not this one. And if you're over here, you're less than both. So it turns out our solution is only the region over here where it's actually less than both, where they overlap. And so none of this stuff is part of our answer. So our final answer is the restricted answer, which is the intersection. And so here it's going to be x value is less than negative 22 thirds. X is less than negative 22 thirds. So in order to be less than both of these, you have to definitely be less than 22 thirds. And so that's our final answer. Sometimes you'll get an and statement that causes you to have an overlap. So sometimes if one of these is going that way and the other one is going that way, your answer will just be the region in between where they overlap. But if they're both pointing the same way, whether it's to the right or whether it's to the left, if they're both pointing the same way, then the region where they overlap is just going to be one or the other of the inequalities. So just be paying careful attention to these. And notice that, this problem, it took quite a bit of work. We had to solve this inequality. We had to go over here and solve this inequality. We had to draw a graph. And then we had to logically think about where those two things are going to overlap. So these problems, you're going to have to write down the problem. You're going to have to show a lot of work. They're not going to be something that you can just scribble down an answer in a few lines. So take your time, be methodical, and do a good job on these. Okay, our last example is an or statement. So remember, for an or, either one or the other could be true. So we're looking for the union of the two solutions. So let's solve this one first. Minus 1, minus 1. 4x is greater than 9. Divide by 4, divide by 4. X is greater than 9 fourths. That's one answer. And then we have a big old or. Solve this one. Now we could multiply the 5 in, or we could divide by 5. Now, because I have a 15 over here and a 15 is divisible by 5, I'm going to choose to divide by 5. So these cancel. I have x plus 3 less than or equal to Negative 15 over 5 is negative 3. Now I can subtract 3. Now I have x less than or equal to negative 6. Again, you could have distributed and then solved. That would have worked just fine. But because I noticed that they divided evenly, I chose to go that route. So we want to find where this is true or this is true. So we can make our number line. Put in your 0. Put in your negative 6. Put in your positive 9/4. Notice that I'm not drawing it to scale, but I am labeling all the important points. That's the part that matters. When you're looking back at this, are you going to understand what inequalities you're graphing? Yes, as long as you label these points. Okay, x is greater than 9/4, not including the endpoint, so an open circle and shading this way. And then over here we've got x is less than or equal to negative 6, so open circle, shading this way. Okay, anywhere either one of these is true is my solution. So all of this is part of my solution. All of this is part of my solution. So this really is just my final answer. There's nothing that changes by realizing how the graph is. Now, something that you could consider is, what if I had an OR statement where one of them was going this way and the other one was going this way also? Then this solution here encompasses everything that this one is doing, and so you might have to only include, or restrict your answer so it's not redundant. If you say x is greater than 5 or x is greater than 6, well, you didn't have to say x is greater than 6 because everything that's greater than 5 already includes all the possibilities that are greater than 6. And then sometimes you have an OR statement that looks like this. So you have one going this way and one going this way. So this one covers all the negative numbers. This one covers all the positive numbers. So collectively, these two combined says all solutions. So it's possible with an OR statement to have everything. Just think about it like this. If I say everybody older than 10 gets in for free, and everybody younger than 20 gets in for free, well, there's nobody who doesn't at least meet one of those conditions. Everyone is either older than 10 or younger than 20. There's no way you could not be at least one of those two things. So when you're doing these different solutions and you're plotting your graphs, make sure you're being mindful of if it's an OR, your answer is getting bigger. If it's an AND, your answer is typically getting smaller. Alright, that's it for this one.